All right, Physics 2, welcome back to part 2 of Monday's lecture. And we're going to start off with an example. So we've just had our mind blown about just how amazing light is and how we have, you thought you were looking at electric and magnetic fields. Oh, you were doing so much more than that all semester. I know I've said this before. This is why I enjoy the build approach to the Physics 2 class. I like building in all of this understanding so that we can get to this with a really nice complete picture in our minds. I mean, there's more than one right way to teach the course, but this is why I'm really partial to just slowly putting these puzzle pieces together, and it's like building a tower. It's great. Okay, so we're going to do an example. So we have an electron traveling yes, it is electron. I've crossed out and rewritten and crossed out what particle I wanted to do. Electron is what I want to do. Actually, let's be more exciting. Let's do a mu minus. Come on now. At non-relativistic speed along Z in positive Z in a region of nearly zero fields. At t equals 0, it reaches the origin and enters a region with an electric field 5.2 times 10 to the 16 volts per meter. You observe fields at location 530 meters. Okay, so a couple things I want to note. So here is the electric field. We know that we're going to start our time when it enters the origin. And please note, this is traveling at a non-relativistic speed. So charged particles are going to travel at whatever speeds they're going to travel at. Sometimes it's relativistic and sometimes it's not. Fields travel at the speed of light. Charges can travel at any speed, limiting up to the speed of light. So make sure that you're being very careful to determine, are you dealing with the speed of a field or are you dealing with the speed of a charged particle? So we want to answer the following, and I'm going to list it all out and then we'll do it. When do you first observe radiation? So you're here. When do you first observe radiation? Then we're going to make a diagram of the direction of the initial radiative electric field and then actually we'll address this in part B too, but make a diagram of the direction of the initial radiative magnetic field Then we want to look at the magnitude of the initial radiative E field at observer location. And magnitude of initial radiative magnetic field. All right, so a lot of setup, and we're going to walk through each one of these. So basically, all of those equations we've just been deriving, we're now going to apply them. So here's what's going on. One, two, three, four, five. 1, 2, 3. You are here. I should really draw in like the Google you are here thing. That would probably make more sense. Okay. Part A. To get distance, here is the origin. 0. Vector. To get the distance, we need the magnitude of r, and then we need to divide by v to get t. So t is equal to, we're just going to do this in one step because we are very good at doing vector magnitudes. 5 meters squared plus 3 meters quantity squared, all under a square root, divided by our velocity of the field, which is 3 times 10 to the 8 meters per second. So if we think back to part A, when do you first observe radiation? Not when do you observe the particle. Radiation travels at the speed of light. It's like it is light or something. 1.9 times 10 to the minus 8 seconds. And for light to propagate from the origin to the observation location. So you first detect light, then you probably have a little PMT, photomultiplier tube, light detector. Okay, so 1, 2, 3, 4, 5. Wow, I'm really good at this. And by that I mean I'm not at all. Okay, so we've got, here we are, V, we've got E rad, B rad, all here. So E minus decelerates in positive Z, so A perpendicular is in positive Z, and minus Q A perpendicular is equal to minus, 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 just 2 minuses. A perpendicular is in plus Z as shown. And that also answers C. So this is the diagram that we're looking at, or that we're looking for in something like this. All right, moving on. Part D. magnitude of initial radiative E field at observer location, and then part E is going to be the magnitude of the initial magnetic field at observer location. All right. Speed is non-relativistic. So A perpendicular is equal to A is equal to E over M. E radiative, 1 over 4 pi epsilon naught. And we saw this expression, of course, all the way back in chapter 13. E, charge E times E divided by M over C squared R. We're looking for magnitudes, that's why I've dropped my negative signs. E radiative, 9 times 10 to the 9, Newton meters squared over coulombs squared. 1.16 times 10 to the minus 19 coulombs, quantity squared. 5.2 times 10 to the 16 volts per meter. 3 times 10 to the 8 meters per second, quantity squared. Square root 5 meters, quantity squared, plus 3 meters, quantity squared. And then also on the bottom is the mass, 9 times 10 to the minus, oh shoot, I forgot there was a mass in here. Okay, this is now an electron, not a mu minus anymore. Serves me right for changing things on the fly. E radiative is equal to 25 volts per meter. And for B radiative, B rad. Oh man, that's a good rapper name. B rad is equal to E rad over C. It's equal to 25 volts per meter over 3 times 10 to the 8 meters per second. B rad, B to the RAD is 8.33 times 10 to the minus 8 Teslas. Yeah, that's right. I wrote that. Be jealous. All right, so couple key points. Of electric and magnetic fields. Fields made by charges so minus Q is at rest. So you have a 1 over R squared E and no B field. Sorry, 0.1. Do that instead. If Q has a constant velocity, then you have a 1 over R squared E field and a 1 over R squared relationship to the B field. So basically, I'm summarizing everything we've learned in Physics 2. Q with a time-varying velocity, so in other words, an accelerating charge, then you have a 1 over R E field and a 1 over R B field, which is how we see the stars. All right, so here's where I'm just gonna a little teaser of like stuff you can do. And if you take an electromagnetism class, unfortunately you can't take it here because we don't offer it. You get to do E and M with magnetic monopoles, which are entirely theoretical and probably don't exist. But Maxwell's equations work with them, which is very interesting. So fields made by magnetic monopoles. So if your little M particle is at rest, then you have a 1 over R squared B no E field. If your little m is at constant velocity, then you would have a 1 over r squared B field and a 1 over r squared E field. And if you have a magnetic monopole and you accelerate it, so it has a time-varying velocity, you have a 1 over r B field and a 1 over r E field. There you go. All right, I think this is a good place to stop. We will get into light waves in our next lecture.